Okay, I'm going to give you the formal definition of what a polynomial function is, and it's going to look really scary, and it's going to look really ugly. David, you ready?
No, I don't have any paper.
Okay, so like I said, it's going to be the function itself. The actual definition is going to look super gnarly and super scary, but I'm going to try and break it up for you. So just don't freak out when you see it, okay? But here's the formal definition of what a polynomial function actually is. So it's representative like this. F of x equals, okay, a sub n times x to the n. The n is in the exponent. We're going to add to that the next term, which would be a sub n minus 1. So just the next term down the line. X to some exponent, n minus 1. And you just keep on going like this until you get to the last couple of terms, like, say, a sub 2, x squared. And then how about a sub 1 term, x to the first, and then some constant term on the end, a sub 0. All right, so let's talk about what all these things actually are, okay? So this is a representation of a generic polynomial function. First of all, let's start off by talking about these pieces down here. This part right here, this part right here, this part right here, all of these little a's out in front, these are just real numbers. This is just some real number out in front. And they have to be some real number. And even this one over here in the end, some real number. All right? So those are just numbers. All right? The n, which you'll notice is right here, the exponent, that is going to be the highest degree term that there is on this thing, because you'll notice all of the other ones, the n minus 1, the 2, all the way down to the 1, they're all shrinking. So the biggest one comes first, and we call that the degree of the polynomial. So it's the highest degree term. So as an example, if that was a 5, it'd be a 5th degree polynomial. If that was an 11, it'd be an 11th degree polynomial. If it was a 2, it'd be a quadratic. Okay, it's coming back to you, right? This part in the front, this thing right out here, the one that goes with the degree, that one, this plays a very special role. This whole entire thing, right, this is called your leading coefficient. All right, a couple of things that we have to know about the n, all right, to determine it. A couple of things to know about the n. N must be a non-negative integer, and the symbol for integer is that, the funny z, right? So n has to be a non-negative integer, so a positive integer, and we also noted that n is the degree. Yeah, non-negative, they're positive integers, okay? So what I'm going to do now is I'm going to give you some examples. I'm going to give you 2 examples here. I'm going to give you examples of polynomials that do represent polynomial functions, and I'm going to give you examples that do not represent polynomial functions. And I want to see if you can tell me for what reason it is or it isn't, okay? So for the first one here, I could give you this polynomial. F of x is equal to 3x to the 5th plus 7x to the 4th plus the square root of 2x squared. Okay, that's a polynomial function. Let's go through and talk about why this is a polynomial function. Okay, this number right here, that number 3, that coefficient, is that a real number? Yes, it is. Good. How about the number 7? Is that a real number? Yes, it is. Good. How about the number square root of 2? Is that a real number? Yeah, it's an irrational, but it's still a real number, right? So far, all of those match the criteria. Okay, let's look at the exponents. Is that a non-negative integer? Yes, it is. Is that a non-negative integer? Yes, it is, and of course, that is too. What is the degree of this polynomial function here? What would it be? 5. This would be a 5th degree polynomial. It's the highest degree term. You guys good so far? Let's take a look at an example of one that is not and see if you can figure out why. Okay, here's number 1 for this one. Let's give you f of x is equal to negative 3 square root of x plus the square root of 2x to the 3rd plus 5x squared. Okay, for some reason I'm telling you that this is not a polynomial function. What is it? Well, let's go through the analysis. Does anybody see it so far? Let's hear it. This, negative 3, is that a real number? Sure is. Square root of 2, is that a real number? Yep, is that a real number? Yep, so it must have something to do with the exponents. What's the exponent here? Very good. This can be written as negative 3x to the 1/2. And is 1/2 a positive integer? No, it's not. Therefore, this is not even a polynomial function. Do you guys see it? Okay, let me give you another one here. We'll do a couple more because I want to make sure you get this. Okay, number 2. Let's do g of x is equal to, how about negative 3x to the 7th times x plus 1 times an x minus 4. Okay, this looks a little different, but it still represents a polynomial function. The question I have for you is, can you tell me the degree of this polynomial function? And it's not 7. 9. It is 9. How do you get 9 out of this thing?
Okay, so I remember Miss Gotti telling us like not to multiply it all out, but like you can like there's something.
Yeah. So basically, here's what we want to understand, okay? This term has a degree of 7, yeah? Okay? This term has, the highest degree term will be x to the first. Do you agree with that? The highest degree term will be here x to the first. So I have an x to the 7th times an x to the first times an x to the first. What do you do when you multiply terms of the same base? You add their exponents. So a 7 and a 1 and a 1 would be a 9. So this is a 9th degree. I know it was. Polynomial, okay? Okay, now let's talk about this one. G of x is equal to, how about negative 4 over x squared plus the square root of 2x to the 5th plus 7. For some reason, I'm telling you that that is not a polynomial function. Can you see why? Where is it? Yes, David, you're absolutely right. If I wrote this as negative 4x to the negative 2, right, because this is on the bottom, if I raise it to the top, it'd be the exponent would be negative. This needs to be positive. Okay, when you're taking a look at the graphs of polynomial functions, which we're going to do in a little bit, there are two characteristics that really define them quite well. And the first one is that graphs of polynomial functions are smooth. So what do I mean by the word smooth? They're smooth. That means that there's no jumps, right? There's no holes. There's no gaps. There's no corners. Okay, they are just really, really smooth. There are other words that describe them, but the main idea is that a polynomial function is really, really smooth. It's also continuous. What do I mean by continuous? It means it never breaks. It never breaks up. Okay, so here is an example of a nice, smooth, continuous polynomial function. It looks something like this. Okay? See, I just made that up. See how it looks smooth and curvy and it's continuous and it goes on forever and ever. It's all good. Here's an example of one that would not be. All right? And you'd be tempted. It would be a function. Okay? What's wrong with that one? Why is that not? Is it not smooth or continuous? Which one is it not? It's not continuous. There's a hole in it, right? It's not it is kind of smooth. Maybe all those words belong down here, right? By continuous, jumps and holes and gaps. Maybe all those belong down there, right? I guess corners could be used for smooth. But regardless, this thing has a big gap right here, right? Big, huge gap right here. So that would be an example of a graph that is not smooth or not continuous at the least. You guys good with that part? Here's what we're going to do. I'm going to give you a bunch of information. We're going to make a little chart here, okay? So how does end behavior of a graph and the leading coefficient test work together? So here's what I mean by this. Let's say we have a function. F of x equals sum a sub n x to the n. And then we have some stuff after it, but we don't care about the stuff after it because, after all, this part, all of this is going to be our leading coefficient. This is the thing that we want, especially this a sub n. So that a sub n being the leading coefficient, it has to be a real number, but it has two choices. It can either be positive or it can be negative. You guys agree with that? Real numbers are positive or negative, as long as it's not 0 for us, okay? So what we're going to do is we're going to make a chart. So we're going to talk about positive, and negative here, and then positive and negative here. Okay, so I have this chart going on. Well, let's take a look at the exponent. Okay, this exponent here, this n, well, we know it has to be positive. It has two choices as well. It can either be an even positive, or it can be an odd positive, right? So this can either be even or odd. Okay, so here's our graph. We're going to have the combinations of what does it look like for positive and odd? What does a function look like for negative and odd? What does a leading coefficient for positive and even do? And what does a leading coefficient for negative and even do? So these are all possible combinations that we could have. Okay? So an example of a positive odd polynomial function would be something like, how about f of x is equal to 5x to the third? That's positive and odd. Positive because the number 5 is positive, odd because 3 is odd. Give me one for negative odd. Can you make one up? Negative 5x to the third. Okay, so that would be an example of negative and odd. Can you make one up for even? Positive and even?
It's 5x squared.
Okay, 5x squared. Okay, that's positive and even. Can you give me one that's negative and even?
Negative 5x squared.
Okay, you want to do negative 5x squared. Well, let's go to the fourth just to change things up a bit, but still even nonetheless, all right? Okay, can you remember these for me real quick? Because I'm going to switch over to fluid math and we're going to try them, okay? So let's talk about the one that we had first was 5x to the third. Okay, so when we graph this, here's what we're looking for. We're looking for end behavior. So we're looking for what is the graph doing on this end and what is the graph doing on that end. So how would you describe that? Up and down, right? So this is kind of like down on the left and up on the right. You guys agree with that? Okay, so this would be, this graph would look something like this. Down on the left, up on the right. Yeah, go ahead. What are you going to do? Okay. So we might say down, left, up, right. Okay, how does that compare to something that's negative and odd? Negative 5x to the third. What would this thing be doing? Oh, well, look at that. That's going down over there and up over there. Okay. So this one is going to be looking like the opposite of that. It's going to be looking like this. Up on the left, down on the right. So up, left, down, right. Is this making sense so far? Okay, we only have two other combinations here. They could either both be going up or they could both be going down. Well, what's your guess for end behavior? For even and positive and even? Yeah. This is going to look something like this, right? Up on the left and up on the right. And then think about negative and even. What's that going to be? Down on the left, down on the right. Okay, so if I give you this one as an example, x to the third plus 5x squared plus 2x plus 1. All right, and I'm interested in knowing its end behavior. Well, taking a look, I could see that this is going to be a positive and odd, right? It's positive because the leading coefficient is a 1, and odd because I have a 3. So positive and odd is going to be doing what? Down left, up on the right, okay? So let's actually graph that thing. What was it going to look like? What'd I give you?
X cubed plus 5x squared plus 2x plus 1.
5x squared plus 2x plus 1. Okay, so check this out. Did we get it right? What's the end behavior? I always said down on the left and then up on the right. Now there's definitely some stuff going on in the middle, right? But we're just talking about the end behavior. So the end behavior is going up on the right and it's going down on the left for the end behavior. We're going to talk about that middle stuff in just a moment. Okay, example B, negative x to the fourth minus 4x squared. What do we have for the leading coefficient test? Well, let's look at the leading coefficient there. Well, let's see here. We're going to have negative and even. Okay, what do we know about negative and even? Negative and they're both going to be down, right? Something down like that. So negative x to the fourth minus 4x squared. What does that look like? Y equals negative x to the fourth minus 4x squared. So here we go. Check it out. Definitely down on both sides. You guys cool with that? Okay, let's try something a little more interesting. Okay, what do you think about this one for part C? What's the degree of this? Yeah, not 5. You're close. The degree is 6. How do you know the degree of this thing is 6? Yeah, because okay, this one we have an x to the third. That's our highest thing, our highest term. This one will have the highest term of x squared. This one we have the highest term of x to the first. If we add all these up, we get an x to the sixth. Sixth is an even, so I have a negative out in front, so I'm having a negative and an even. So what's this one going to be? The same thing as the one before. It just doesn't look like it. It's hidden. Okay, so you need to be aware of that as well. Who's familiar with this word zeros? The zeros of a polynomial. There's a much easier word that you are familiar with, that you know of. You ever heard of this? The zeros of a polynomial? Okay, so let me give you an example. If I gave you the polynomial f of x equals x plus 5, what would the zero be? What does that mean? Negative 5, right. The zero, whoop, that's okay. The zero would be x equals negative 5. The reason it's x equals negative 5 is because when x is negative 5, you get 0 out of the function. Okay? The other word for zeros, you guys, that you all are very well aware of, are x-intercepts. So whenever you see the word zeros, it's the same thing as the x-intercepts. So the x-intercept of f of x equals x plus 5, you'd say the zeros are negative 5. Okay, I bet you guys can tell me the zeros for this next one. If I give you the function in factored form of, how about x plus 3 times x minus 7, what are the zeros in this case? Yeah, exactly. X would be negative 3 and 7. Those are the two zeros. All right, you guys agree with that? Okay, this is where something interesting happens, okay? So let me go here and give you the example, and I'll explain it out for you. So we had this, y equals x plus 5. And you guys told me that the zeros were negative 5. And you'd be totally correct, and look, there it is right there. So let's make this as big as possible. Right? That's the x-intercept. But something happens when I do this, okay? X plus 5 squared. What's the only difference that I've done? What have I done? Yeah, I've taken, what's the zeros in this case? No, not 25. What would the zeros be? What number, when you plug in, would give you a 0 out? It hasn't changed from the first one. Negative 5, right? It hasn't changed. But something with the graph has changed. Take a look. So the 0 is still at negative 5, right? But because I have a squared term there, what the graph does what? It turns around at negative 5. Do you see that? So what would happen then? What do you think is going to happen if I do this one? X plus 5, and I cube it. What's the zeros? Negative 5 is still the 0, right? But look what happens. So what's going on here? There is something that's happening here. It does level out, right? If I zoom in on this thing, you can see, if I zoom in really close, there's still only one 0. Even though, like, see all this space right there? It just gets flatter around that 0. Yeah, the graph turns for certain exponents, and it goes through for other exponents. I'm wondering if you see the pattern here. Which one's which? So here, I'll give you an example, okay? I'll move this over, and I'm going to give you this. Y equals x plus 5 to the 4th. Okay, what's the 0 going to be? Negative 5. Is it going to go through negative 5, or is it going to turn at negative 5? What? Turn or go through? Here we go. What's it do? It turns. It just gets a little flatter, right? The higher the exponent gets a little flatter. So the whole point of this, so what's this one going to be? We'll do one more. We're looking for a pattern here. X to the 5 to the, let's go to the 5th. Yeah, the 0 is still going to be a negative 5, but look what happens. It actually goes through. You can't see it. The orange one, right? Okay, so what are we summing up here? What are we saying here, right? We're saying that for any degree, like this is a first degree, if I have an odd degree, it's going to go through the x-axis. Look, odd degree, it goes through the x-axis. Odd degree, it goes through the 0. Even degree, it turns around at the 0. That's what we're trying to get at. Yeah? Okay. So let's write that down, then we'll do some more examples. So This is actually the sixth box. Okay, and this is called multiplicity and x-intercepts. Alright, so here's what we just sort of put together in our little idea here. If the degree is even, then the 0 will touch and turn around. If the degree was odd, then the 0 will cross. Whoops. Okay, here we're getting to this idea here. If I give you a polynomial function, this one happens to be in factored form. I have a 1/2, I have an x plus 1, then I have a 2x minus 3. Can you list all the zeros here just by looking at it? Yeah, what are they? What are the zeros going to be? Yeah, x is going to be -1. What's the other going to be? -3/2, right? -3/2. Okay. So let's see here. If I call this 1, then I'd have to call that -1. And if I call that 2, then I'd have to call that -2. Okay. So at this particular 0, at -1, what's the degree of this term right here? The degree is what? 1. So what do we look here? If the degree is an odd number, it will do what? It'll cross through. So at that particular 0, at -1, my graph will cross through here. So I'll have some kind of a cross through there. At this particular 0, the exponent is what? Even, so it's going to have to turn around at that particular point. So if I go to this would be +3/2. Thanks. At +3/2, so 1.5, it's going to turn around at this point. Okay? Now I also know that this whole entire degree is what? The degree of the entire polynomial. This one is a 2, this is a 1, so the degree will be what? Third degree, and everything is positive in the beginning. So I have a positive odd. What do I know about positive odd functions? What do they look like? They go down over here and they go up over here. So some stuff has to definitely happen in the middle. I don't know what's going to happen in the middle, right? But at this particular 0 and at that particular 0, I know this one will cross and that one will turn, and my graph will go up that way and down that way. So what we're actually doing here is we're being able to run an analysis on a full polynomial function just like we did for quadratics, except now we're taking it to this level. Okay? Okay, did you guys see that graph is actually what we came up with? Yeah. Okay, the last little point that I didn't quite mention here, this thing about multiplicity, this 0 has a multiplicity of 2 because it has that turning point of 2. So what if a 0 has an exponent of 5? What would the multiplicity be? It'd be a multiplicity of 5. So whatever that happens, 0 happens to be. So here's what I want you to do. I want you to see if you can make a sketch of this last one. Can you make a quick sketch of this? Well, first of all, find your zeros. Notice what their degrees are. Figure out their multiplicity. It's just whatever that degree is. Figure out if this is an even or an odd or a positive or a negative. So see if you can make a quick sketch of what this is actually going to be. And that'll be our day.